Good morning everyone. Welcome to the exposure to VLSI series. I am Srikanth Neelam and today's topic is basically to go over the post manufacturing tasks. Over the series you might have gone through different phases of design, verification, physical design, analog layout sessions, and today we are going to take off from the time when the manufacturing is completed and the wafer is out. Okay. So for a product to be really successful, there are various steps which involve from post-silicon, from time the wafer is ready, where it has to be taken to assembly house to assemble the die on the substrate and then assembled on the board and then done various amount of testing before a successful product is delivered to the end customer. So in this process, let me go over a couple of steps at a very brief level, where we are going to cover the process first and then the test procedures. So from the today's agenda, we will go over the design to product process, and then from design to product, the various test procedures that are involved. We will take a sample design to understand how design can be, or various challenges are posed for the design in post-silicon phases, or when you are trying to apply it to the real world. And then we will conclude with our so far understandings. From the moment the wafer is ready, there are quite a few steps which are involved. So we know that for the wafer is in a circular dimension, and one wafer consists of lots and lots of dices. So the first thing that has to be done is a process called back grinding, where the thickness of the wafer is actually reduced in such a manner that it can fit into the silicon package comfortably, and also for stack up purposes, you want to, when multiple dies are stacked up, you might want to control the thickness of the wafer. That is called back grinding. The second process is where you basically slice the wafer and come up with various we cut the wafer into multiple ICs or ASICs. So that is the second step, where you can see that the wafer, which is circular in structure, is sliced through a saw, and then you derive your different wafers, silicon. From a design to products process, the next process that is involved is the substrate assembly. A substrate is a PCB, a very compact PCB, where the die is assembled over it. The main reason to have a substrate in between, without the die not having directly onto the board, is to reduce the cost of the board. The board basically has a lot of other components, but a substrate has only one silicon. There are two main dies types. One is called wire bond, one is called a flip chip. In the wire bond, as you can see in the diagram here, the wires are basically taken from the lead as a top and then mounted to the substrate, and the substrate has the bottom balls, which is called a ball grid array, which makes contact to the actual physical board. The second type is called a flip chip, where the bumps actually are directly connected to the substrate. So complex designs which are running at very high speeds, the bumps are directly connected to in a flip chip format. Some low speed interfaces, or if you want to reduce the die cost, substrate assembly cost, you will basically go for the wire bond. The next process is basically, once your die or the silicon is ready and packaged into a housing, we want to put it onto a real application platform, and for the application you have to go through different phases, which are called schematic, where you actually realize the end product requirement and house the different components apart from our silicon and make it into a complete system. So schematic is a place where your design components are all added at a schematic level, and then on a layout phase, where you basically really physically draw the different routes on the board, putting all the components on the board. So once the board is manufactured, you have again go through various assembly processes similar to the substrate, where you prepare a stencil so that you can put the solder paste throughout the entire board in one go. And you have a pick and place machine which actually takes every component. We have very advanced pick and place machines right now which can take around 50,000 to 60,000 components and place them in one go. That means if you want to really produce millions of components on boards, these machines are really automated with the XY coordinates. They basically take every component and put it on the PCB. And once the component is placed on the PCB, you go through a reflow machine where the complete soldering is completed. So now after this entire process is the assembly happens of the board, and then you will be able to realize a product. And from electronics point of view, obviously the end products can be anything. It can be an automotive platform, it can be a consumer platform, or medical and IoT. The number of domains may be are not at all limited. Like for example, consider an automotive, right from infotainment system to the safety measurements, and now with ADAS or the automatic driving concepts, electronics is going into everywhere. Like the medical devices, with the recent COVID, a simple pulse oximeter has literally saved a lot of people. And it's a very simple design as such, but it was very handy for at an end user level. Consumer electronics we use in our day-to-day life, and these are some things that we cannot live almost. And home automation is the next one, where you literally have a lot of automotive automation within the home to make our living very comfortable. So given that there are so many numerous applications that electronics or the VLSI or embedded systems can be applied to, let's come up with a simple thought, like just to understand this process more in detail. We'll come up with a simple design, like we'll try to conceptualize a small design which can consist of a processor. In regular any system which will require some kind of an embedded system or a software will require a processor, and typically let's take an example, it's around 1 GHz. And a processor to run properly, obviously it will require some kind of RAM and a ROM. I'm just trying to list few components here. The reason to list these components here is to walk through how each component has different challenge to meet in the real life. Okay, so a processor, if it's not meeting 1 GHz, your product is no longer going to be useful, right? So even if you meet 900 MHz, you're literally not meeting the specification. Memory, suppose I'm talking with respect to DDR, we are basically talking about 2400 MTS. Okay, if the memory speed is not as what you required, again your product performance is impacted. Storage, again here also, if the storage speed is less, most of your video playback or image captures, they don't really work. I listed few basic peripherals like an ADC, where most of the sensors are integrated. Just imagine you are trying to interface to a sensor which requires a high precision voltage like measurement through an ADC, analog to digital converter. Now if I have error in the ADC, you will be literally reading wrong values. Like imagine the pulse oximeter, the value from the sensor is wrong, you will literally report wrong values. So you really don't want to scare anybody there. From other interfaces, external interfaces, let's take an example, USB, which everybody knows of. There are like different specifications of USB. I'm taking an example of 5 Gbps, okay, which is the USB 3.0 specification. This specification allows you to transfer rate at 5 Gbps. Anything even less, around 4.9, the specification would fail the protocol compliance. Okay, and let's talk about simple GPIOs, which are IOs which are used to maybe control your LEDs and maybe control other peripherals on the board. So this is a very simple design, but as such poses lots of limitations and requirements from an end product point of view to make it successful. So our interest here is to understand what are the different challenges at a post-silicon level or in a real life product integration level. The design will be put to test, where you want to understand that if those care is not taken care quite earlier in the design cycle, your product development cycle or the time that is taken to we call it as TTM, the time to the market is heavily impacted, and a delayed product sometimes may lose the market, and obviously you might the entire purpose of the product might be lost. Like for example, just take this COVID pandemic. There were quite a few electronic components or equipment which were required in the market, and if they were not available, you would never meet the requirement. So now that we have discussed about a sample application, let's talk about how the sample application really gets impacted and what are the different factors that are involved. We know functionality is one of the major important, okay, and functionality which all is basically to say, like for example, I'm just simply talking about a processor. A processor is fetching the opcodes and executing the instructions. So that is very clear and simple. That's at a functional level. At an interface level, you're talking to the external world. Okay, so there are two major reality checks that we need to really think about at different phases, and one is called signal integrity and second is called power integrity, and these two beyond functionality prove or showcase the robustness of the design. We might have seen many components or products, electronic products, which are not up to the mark. They might crash frequently, or they get heated up a lot, and sometimes they don't really play or meet the requirements, and under stressful conditions they really fail to perform. And that these all are differentiation factors when you're trying to select a product, which is a good product and which is a bad product. You'll simply say, okay, my performance is not up to the mark, my power backup is not up to the mark, okay, and the price is too heavy, we can't purchase it, right? And why all these factors are basically impacting the product? From a business point of view, they make a product successful or failure. So those are the user level experiences, whereas from a implementation point of view or a design point of view, if you want to understand what are the parameters that are really disturbing apart from the functionality is a straightforward pass or a fail, but there are some parameters which impact over a period of time. Like for example, signal integrity. Signal integrity, like in this particular diagram, we are talking about this red particular line shows a ideal waveform, okay, where the above green line shows above this one is a high and below this is a low signal, okay. But in reality, the signal is like a black signal where you basically see some amount of overshoot, undershoot, and there's some distortion of the signal. So obviously the reality of this signal is actually impacted. The reason, because we have a big channel. The channel is called, right from the buffer, which is on the silicon, which is on the die, has to connect to the substrate. The substrate connects to the board, and the board, maybe if you're trying to connect to USB cable, it goes through the cable and then to the receiver. That means we are adding lot of parameters in between the actual design and the actual receiver, and the signal is going to go through all these different channels and is going to definitely get impacted. And in this process, the distortion of the signal will directly impact the functionality or the performance at the minimum. Like for example, I am operating this CPU, and if we are thinking that the CPU or the design process is not up to the mark, then the frequency has to be reduced, okay. So that means the performance is reduced, okay. So similarly, there is another parameter called power integrity, right? Power integrity is basically nothing but to ensure that whoever is the source of the power and the destination of the power, how much is the difference? Like I'm sourcing the device 1.8 volts, but at the design level or the die level or the silicon level, you are receiving only 1.5 volts. That means there is a drop of almost around 0.3 volts during the medium, and the medium or the channels that we have is from the power source is we have a board, we have again the substrate or the solder paste and other components in between, like the bypass capacitors or the inductors, which all are like channels in between this power source and the actual silicon. So literally, if you might have designed the circuit to operate at 1.8 volts, there are very high chances that you won't get the 1.8 volts at all, right? So that means you have to design your circuit to make sure that you basically are able to accommodate the differences of the voltages, sometimes we basically say we have a tolerance voltage of plus or minus 10 millivolt or 10% of the actual voltage requirement. Okay, so so this again, power integrity point of view, these losses and everything are directly impacted based on your power or the battery performance, right? So the more the power requirement is there, the battery will be drained fast, and obviously the power is directly again connected to the performance. So if the performance, like if you want to increase the frequency, that means it is more power hungry. So you definitely have to increase the take very good care about this power integrity to ensure that there are no losses in between and you're getting very good power to your actual design, so that the design can perform at the best performing frequency and deliver the required output. So signal integrity and power integrity are one of the two major parameters which actually give the robustness of the design. Now after we talk about this, let's get back to our design. Now our design, which has a microprocessor and it has some memory, it has some interface like ADC and USB. Now once the design is manufactured at a wafer level, the first thing that happens is at a wafer level itself, you want to sort out which wafers are good, which wafers are bad. Obviously during the manufacturing process there might be defects that have been there and they have to be ruled out, because there is no point in assembling faulty dies, right? So once the wafer, so basically there is a process called a probe, like there's a wafer probe which is available, where the probe actually reaches up to each die on the wafer and you apply patterns like here, which you can see. We call it as a scan chain test or a memory BIST. The scan chain test is nothing but it basically goes through all the flops in our design so that the loop is closed. That means you are basically checking that all the components on the board or the different modules that you have on the silicon are all interconnected well and are functioning okay. So that's from the scan chain. Memory BIST is basically a inbuilt. BIST is called built-in self-test, which basically performs the memory reads and writes for smaller blocks of memory, and it gives you the result, whether it's a pass or a fail. So these two are very basic checks, at least to check the sanity or the health of the silicon. And then the product, the die is, or the die or the ASIC is basically after the dicing is good to assemble into a substrate. The same test or some more test can be added to this test suite at a substrate level. Now for a substrate there's something called an ATE tester, where you will put all the assembled substrates which are packaged already and you put them to the same test. Again you do the same sorting tests. So there is a procedure called binning, where you are trying to understand whether the silicon, if there are any defects in the silicon. Sometimes 100%, if there are like some basic errors like short errors or like stuck at fault errors, you will simply have to discard the design or the silicon. But if there are any minor issues, like for example one of the IO is not working properly, or basically the speed of the operation is not up to the mark, you'll move them into different bins to understand why those errors have come. And those errors are mostly manufacturing related and they have to be fixed at the manufacturing level. Now basically there are more and more tests which are performed at wafer level to understand whether the silicon is fast, slow, and which corner it belongs to, because it directly tells you whether the actual performance of the silicon will be slow or fast when compared to your design specification. Once the substrate level screening is done on the ATE, the next one that happens is at your board level, and what we call here is a validation. At a silicon validation level, there are a lot of steps which are taken or performed to ensure that the design is very good and meets all the requirements which are required for a successful product. For example, in our design, when we talked about the processor, we want to first ensure that the processor is functional, That means it is able to fetch all the instructions and execute it from our different memory medias. It could be DDR, or initially there will be a boot ROM, and then it will basically fetch the operating system from a storage media like SD card, and then execute or to copy the operating system into the DDR and run the operating system from the DDR. And what is the maximum data rates we are able to achieve at the processor level? That means one processor, it can be mentioned that the processor is measured at a part of MIPS. That means million instructions per second. How many million instructions is directly again related to frequency. Frequency is again related to the performance of the silicon, and obviously performance of the silicon with respect to both signal integrity and also with respect to the power integrity. So from a simple CPU standpoint of view, there are various tests which are there to ensure, like dry stone test is available to ensure or to understand how much is the performance of the silicon. And let's take another example of memory. For memory, obviously read and write is one basic check that people can do, that everybody can do to ensure that the memory is working, but the memory also comes with a lot of defects, and especially the high speed memory interfaces like DDR, they have a lot of signal integrity challenges because they have to talk to an external component on the board, and DDR is a parallel memory bus which has a lot of signals to be connected. Like for example, a 64-bit interface, that means all 64 lines have to be connected or like having the same amount of delay to ensure that the 2400 MTS is whatever the requirement is meeting properly. So sometimes if there are like signal integrity issues or the power integrity issues are there, then we may not be able to reach the required data rates, and that is directly that's directly impacting the performance again. So processor and memory are two major things for our embedded system software point of view. Now let's talk about other interfaces like simple GPIO. For a GPIO at a functional level, you are talking about simply toggling it to different states, like taking it to one state or low state. But even for a GPIO, there are a lot of other parameters, electrical parameters, which are covered as a part of characterization. Functional testing is validation is more of functional testing to ensure that the design is working as per the specification. Okay. Protocol testing is like, for example, USB. USB has a standard, and it comes up with a specification, and every design has to meet the specification, and only then the product is going to be allowed into the market. Like for example, just imagine you have got a pen drive, and that pen drive has to work everywhere. We cannot say that this pen drive will work only with computers, not with mobile phones or media players. That's not acceptable, right? So obviously we have to have a lot of interoperability and a lot of compliance testing which is there, which are all covered as a part of protocol. So most of the interfaces, like external interfaces like USB, PCIe, or DisplayPort, HDMI, all have different standards, and they have different compliances to be passed before we can confirm that the product is really good to go into the market. Performance testing, again, as I mentioned, from the CPU point of view, we definitely have to ensure that the CPU is meeting the at speed requirements, and also the entire system has to work within the power budget. Now we have met the performance, but we are broken or leaking a lot of power. That means the product is again not going to be satisfying the market needs, which is again going to be like causing a big setback to the product. Okay, and then validation as such ensures that the end system level requirements are met in the lab itself. Like for example, let's talk about this same design that we have chosen, and we are integrating it to a sensor application. That means we are going to create a real-time use case scenario to ensure that the functionality is not broken, and we can run it overnight and multiple days also together to ensure that the functionality is intact and there are no system level crashes or are there no functional level compromises in functionality. Like for example, in the example that we have taken, I'm just taking an example where the sensor data is fed to the USB. That's a simple application we can talk about. But the data path involves going all the way from USB, so from ADC, which reads the sensor data, and CPU, which does the processing, memory where the result is stored, and from there it goes to the USB for say for example record or storage. Okay, so we have to create that entire scenarios, which is mostly have to be the superset than what the end customer is going to use. That means the end customer may use only few features, but from a validation purpose, we are literally ensuring that all the design features that have been implemented by at the design phase have been tested, and we know what are the faults, and we also know what is the boundaries of functionality. In this process, if there are some faults, we might have to have or add software hacks in place or patches, so that the functionality is not broken and the end user experience is met. The next phase we can talk about is called characterization. In characterization, we are trying to understand the margins of the design. Okay, like for example, how good the design is going to work across different conditions, like it could be the process. In the wafer manufacturing procedure, we discussed or we went through a little bit called a slow process and a fast process, which actually impact the rise times and fall times of the at an IO level. Okay, so the process is a variation which will directly have an impact on the performance of the design. And then the voltage, as I was mentioning, because of power integrity issues, you give a lot of margin in the design to ensure that we are, even if there is some additional voltage or some reduction in the voltage, you will be okay to manage it from the design, will be is good to work. And also temperature. Across the world, the temperatures are not expected to be common or like uniform. Room temperature approximately we say is 25 degrees, which is the ideal temperature. But there are from an extreme conditions, if you want to verify the design is good, we can literally test the design from minus 40 degrees to plus 125 degrees. It does not mean that the real outside world is so hot or so cold, but it means that because of the additional components on the board, the entire ambient temperature goes up. Like even in room temperature of 25 degrees, if there is a lot of heat generation components on your product, that means your ambient temperature on the at which the silicon is, the temperature is going to go high. So in short, this testing is called PVT, process, voltage and temperature based testing. So this procedure is performed for all the IOs, especially which are going to interface to the external components and also to the in-house components, like the processor or the in-house like the on-die components, like it could be timers or it could be some other engines that we are going to have. So let's talk about a few examples from let's go back to sample design and let's talk how characterization is performed for CPU. For CPU, as I was mentioning, performance is the key, and we'll take a sample example application or a test which we can run through process, voltage and temperature variations and understand what is the maximum speed at which the processor can work. And that particular test we call it as Vmin and Fmax, where the voltage is tried to reduce, we'll try to go below the actual voltage required, which may go up to minus 10% of the required voltage, and frequency, what is the maximum frequency we are able to go to. So Vmin Fmax test on a standard scenario use case, like for example it could be a dry stone test. So we'll take the dry stone test and apply it on different voltage, temperature and process silicons to understand what is the maximum performance of the CPU. That is from the processor point of view. From a DDR is again a high speed interface. For a high speed interface, DDR is a differential interface and high speed. One of the common tests that we have for DDR or high speed interface signals are we call it as the eye diagram test. In the eye diagram, as you can see, suppose if I'm taking two signals, like two sine waves, and if I'm overlapping on them, you will have this opening, and this opening is called an eye, right? And here you can see that this is the rise time and this is the fall time, and similarly a fall time and a rise time. So when the waveform is superimposed on itself, this is the waveform that this is the eye diagram that we get. And the eye diagram is analyzed by using an eye mask. That means by the opening of the eye, we'll have a small mask here, and if this mask is kind of overshadowed by the design, that means we are not meeting the design specs. Okay, so again we talked about how a signal can be tampered with various parameters when we are talking about the signal integrity. As I was mentioning, the expected signal is like the red line, and the actual reality is the black line here. Now imagine this waveform goes a little bit more slanting. That means you're literally going to close the eye, and that means the performance of DDR will not work at that speed. You might have to reduce the speed of the DDR for sure. Okay, so and again, to the reason why the signal is getting deteriorated is because of the various channels that we have in place. It may not be always because of the design. The design might be good, but because of the channel, the substrate, the board, and the cable, or the interface of the traces on the board, they might have really spoiled the signal. So let's go back to the characterization slide. So as we talked about the eye diagram, similarly for USB, similarly for USB also, which is a high-speed interface at a 5 Gbps, we'll also again do a high-speed eye diagram to analyze whether the signal quality at the receiver end is good, right? So what matters is the receiver. This is called the far end, and near the design is called the near end. The near end mostly is fine. The far end is the problem where we need to solve. Okay, so especially for lengthy cables, like for example USB, the specification says you can use up to 5-meter cable. That means the signal that we are driving needs to go through all the way up to 5 meters and then still be good at the receiver end. So that is the far end test. Okay, so signal integrity point of view, from a characterization we talked about USB, and then we'll talk about another important interface like the sensors, where the sensor I was mentioning earlier require very good precision in capturing the signals accurately, especially the analog to digital converters. If we are saying we are going to be very sensitive, the product will have an advantage or disadvantage. For example, if it is very sensitive, that means there is too many it is going to pick up the noise as well, and the noise sometimes gives you wrong readings, and maybe you will not be able to really use it efficiently from a product point of view. If it is less sensitive, that means the speed of operation is actually impacted. That means if I have to get a correct value or correct sensor reading, it has to meet something called sampling rate. I'm going to sample the actual input data at a specific rate so that you can meet the product requirement. For example, let's take a camera as a sensor. Now if I'm recording a video, and the ADC, which will be again at the pixel level, if it is operating slowly, do you think we can capture the video at high rates or full resolution? That's not possible, right? So the sensor operation frequency and also the sensitivity, that means the resolution of the ADC operation literally defines the entire product functionality. So there are again specific tests for that. So in a characterization terminology, we will talk about characterization. We can say it's something called INL and DNL. These are linearity tests, as you can see in this waveform, where you are basically saying I'm expecting a step of X and I'm getting some result of Y. So a linearity is literally an idealistic approach, but you actually go in steps, because at the end you are basically converting into digital values. Suppose I'm reading 1 volt. The 1 volt will not be exactly 1 volt, it will give you something around 0.95 to say 1.05 or voltage. So we are in this particular characterization, we are trying to analyze how much the deviation of the design is. Okay, so that is from an ADC. So we have talked about the importance of the accurate or accuracy of the ADC functionality and how it's going to impact your design, and also we talked about high speed interfaces like memory or a USB, and understand about how they are going to impact like how the eye diagram analysis actually gives you information that the silicon performance is met or not met. Generally, from a design process point of view, the design is we will say we overdo the design. The reason, because there are a lot of parameters to be taken care. Like for example, if we are talking about the design requirement as 1.8, the design is actually tested or designed for 1.5 volts to operate as well, and sometimes as low as 1.2 volts also. Okay, there are various features called say power gating or voltage scaling, clock scaling, which are actually lot of power saving techniques which are used at the product level. And these features actually are very good tools for software engineers to control and define the product functionality. Like for example, if you want to go to deep sleep mode, you can do something called power gating. If you want to go for complete high-end at speed functionality, you can change the PLL rates accordingly. Okay. So why are we basically talking about validation and characterization when we have different test procedures at wafer level or at substrate level? At wafer level, substrate level, the real-time interfaces are not really possible. Like for example, I cannot connect to a real USB device at a wafer level. I cannot connect to a real sensor at a wafer level. We might be able to do some amount of IO based testing. For example, even for the for GPIOs, definitely we can do IO analysis. Like there are parameters like to calculate them VIH, VOH. That means the minimum required voltage, that is to read as a high or a low. And similarly, the current requirement or consumption by the IO. All these parameters are done at the wafer level and also at a substrate level. We also get leakage parameters at substrate and like wafer level. But when the actual firmware is put and the CPU is running at speed and the real use case is being exercised, that time what is the actual power requirement and whether the real-time onboard regulators are able to provide so much of the current that is required by the silicon, or the silicon is getting overheated, or the performance is not being met. Those are the real tests which are done outside the wafer and the substrate level testing. Okay, so only after this validation and characterization we will understand the strengths and the weaknesses of the design, and that's these parameters. Like for example, from after characterization we can fine tune the parameters, the IO parameters, so that we can meet the actual design speeds. And these fine-tuned settings are actually given back to software, and they are programmed from the CPU in the real final end product. Now, after going through the various validation where you are saying that the functionally you have proven the design, and electrical characterization where you are saying electrically my design is meeting all the standards, after that again there are some more set of testing. So there are various certifications and compliances which we have to pass to confirm that the design is product or the product is can be shipped into the market. So we have talked about characterization and validation, which are impacting at a functionality level, but at an integrated level, that means when I'm putting the silicon on the board with other components or with some user interfaces components, there are various parameters which can literally impact the product actually from design also. One such test is called ESD, which is called electrostatic discharge. Like for example, your product or your silicon, once it goes into a product, and if there is some ESD due to some contacts, it should be able to withstand. That means when the design is itself, all the IOs, the external interface IOs are have ESD diodes in place, which can withstand up to almost around 2500 volts or so. And there are different standards like the human body model, the HBM, or the machine model, the MM and CDM, which have different voltage ratings which are tested. Like you zap, like you can see in the diagram here, where the actual silicon is zapped with around say 800 volts of signal or 2000 volts of signal, and ensured that the silicon is not broken, right, with even after high voltage being given. This is all just given for a very short duration, not for a long duration. Okay. And similarly, there's some another test called latch up. That means if I'm driving a lot of current into an IO, it should not burn out. Okay. Latch up is basically it will get tied up to either 0 or 1. And these tests are extreme conditions beyond the actual functionality. These are real world issues. Okay. Similarly, as I was mentioning, there are a lot of standard bodies and forums. Example here is USB, where we are talking about what they do is the standard bodies or forums, they define the test procedures, and they have certified labs where they will tell, okay, these are the equipments that you have to use, and these are the tests which have to be performed, and the result margins. Like for example, there are USB, suppose if I talk about a sensitivity test, there is a sensitivity margins up to 150 to 200 millivolts, which is the range which is allowed for the sensitivity to be there, and anything below that or above that is marked as a failure. So every standard body comes up with their own test requirements, and after our in-house validation and characterization, we take to the external labs for the certification from the standard bodies. So once the product is certified, that means we have a design which has passed through different levels of wafer level testing, substrate level testing or ATE level testing, and then board level validation, characterization, where you involve a lot of extreme scenarios where you're covering like process voltage and temperature variations. You're testing all those corners, and then you're going to external compliance or the standard bodies or forums to do the or get the certification on the product and on the design. And once all these steps are done at a product level, again you have different tests. For example, certifications, radiation based test limitations, and or like the standard bodies, like we have the FCC and the CE certification. In India we have the BIS certification, which actually define or certify the product is good to go into the market. So that means we have so many phases to be performed before a successful product is launched into a market. And imagine the amount of time that is spent in all these different phases. Let's talk about a simple like the sample design that we have taken. If I have to talk, the only testing phase will be around say 6 months, the design phase another 6 months, wafer manufacturing another 1 month, right? So literally we are looking nothing less than a year time from a design to the actual silicon coming out. And once the silicon coming out and after the testing is completed, the silicon goes to different OEMs, where the OEMs actually come up with their own customized product with the limited features. They may not use all the design features, then they might come with a certain limited number of features, and they stage the product or the silicon for different product levels, from a mid segment product to a high segment product. And that's the finished product which goes to the end customer. So in a short way to say, what we are trying to say that the ASIC design process is a very elaborate procedure, and okay, sure, and it's a very elaborate process and years of time. Like for example, let's take an example of an automotive. Okay, imagine a product which is in the market right now, Okay, that means that product has been conceptualized at least 6 months or maybe 6 years before. Okay, a minimum or at least 3 years before, where you try to come up with what the market requirements are, and then you put the market requirements into a product requirement document, and then the product requirements are translated to design requirements, and the design requirements are again verified at a design at a verification level, and then you have the place and route team doing the physical design, and then there are a lot of analog interfaces. That means every product design or every concept has to be thought at least 2 to 3 years ahead of time. So if we are here in 2021, we literally have to be thinking about what are the products that will be required in the market to be around 2024 or 25, and then start visualizing about it and start thinking about what the market requirements that time will be, what will be the network speeds, what will be the Wi-Fi speeds, and what will be the processing needs, right? And how compact the design needs to be, how much power the design should be able to, like, at low power the design should be able to work on. So all these different parameters have to be thought ahead of time. Okay, so literally, if you can see, I have mentioned the different parameters of design success are, like, people generally the terminology used is called PPA: power, performance, and area. Area translates to the die size, which is again per wafer. If you have some less number of dies, then the area is more. That means the price is going high per wafer. Since the wafer cost is not going to change much, if I'm talking about, say, a $500K or $1 million for a wafer, and imagine if I am getting only 10 or 100 dies out of it, the price of the product is going to be very high. So even if we lose few silicons in this process of the testing, and if the corners are broken, like for example, if my design is not working at the required margins in a slow process, or if the design is failing the performance at a fast process, that means all those dies that have come with the different process levels have to be discarded, and they will be of no good use. That means the yield has fallen. Okay, the yield has fallen not because the wafer process is error prone, but because maybe we have not taken all the measures that we had to take during the design phase itself. Okay, so for a successful product to be delivered into the market, we have to not only think ahead of the market, like around, as I said, minimum 3 to 4 years is the minimum time we should be thinking about conceptualizing the design, and not only that, we also have to take a lot of parameters like the power, performance, and price, and also the time to market. Imagine if we are taking a lot of time to, or we are spending a lot of time in design cycles itself, the product will, even if it comes late into the market, we may not be able to get the margins of the profit which will make the product successful and for the company to be successful. So all the companies outside there are really thinking ahead, planning ahead, and a lot of engineers are putting their brains and to come up with this amazing products. Right now, the VLSI industry is doing amazingly good with lot of like products in the market, and with the machine learning and the cloud computing, the number of opportunities that we have are really numerous. Okay, and in these phases we can talk about we talked about the post silicon challenges, and if we can talk about the design success parameters, I also mentioned about the user experience. At the end of the day, how the user is experiencing product matters to define the success of the product. So for to say that you are a good engineer, you should be able to visualize what a system requirement is. A system requirement, that means at an end level, product level requirement is what it is, and then how to take care of them ahead in the design and be able to meet the specifications ahead, rather than spending time in the different phases of development or different phases of testing. So I hope this session has given you some amount of a peak or visibility into the challenges the actual design has in the post-silicon level, and from the time the wafer is done to the product is actually shipped into the market, what are the different challenges that are posed and how they are tested and how they could have been taken care earlier by doing more thought process at a design level or giving more margins at the design level itself. So I have not covered one major topic, which is obviously the embedded software, which plays a very important role in actually giving very optimistic or optimized performance from the silicon to ensure your battery life is good, and also to ensure that the performance is not compromised. And even if there are any small issues are there from the silicon, the software will try to compensate for that in a way. For example, let's take an example of an ADC. If the sensitivity is too high, what the software can do is add more filtering in the software level and do averaging of multiple results and come up with a different approach, different implementation, rather than directly going towards the or taking the raw values as it is. So there's a lot of care and or I would say it as masking that the software does, and before the very optimized product or a very good performance product is delivered into the market. So without a very good software portion, definitely the design, even however good the design is, you will still not be able to sell the product well. One of the best example I can give you here is the user experience point of view. It's not how well the post sales service is, okay, it's how less the service is required post sales, right? And I think one of the best example that I can give is Apple, which we literally find any service centers, but people really go for the products because they are known for very good robustness. Everybody wants to get an iPhone, which even though it's so costly, because they know that the performance is never compromised and it is very, very good. And at a computing level also, there are companies like AMD or Intel which also have their own share in the market, and they provide very good computing solutions. Okay, so every company marks their own identity based on the products that they deliver. So a lot of for all the engineers out there who are coming out of their college right now, my only suggestion or recommendation is think from a system or a product point of view. Your ideas will be amazingly great, but to realize them into a successful product, you have to think about all the minute details or the difficulties that the design is going to be facing later on, and you have to address it ahead of time. So unless you understand the fine issues or the intricacies involved, the design will be a concept, but it may not be a product. Okay, so that's pretty much I wanted to cover about, and thank you for this opportunity for me to present this session to you, and I hope it has at least given you an insight about the different procedures involved. And I kindly request you to join all the students to join for the VLSI training validatory function from 1:30 p.m. today. Okay, and if you have any questions, you can feel free to reach me on LinkedIn, the same name, Srikanth Neelam, and I'll be more than happy to help you. And yeah, that's pretty much I wanted to cover up on. Thank you.